Swayam Prabha. Digital India. Educated India.
So, see, we have already seen that we have to work with matrices, a lot of them, when we talk about symmetry operations. And at the risk of boring you by saying the same thing again and again, the reason why we need matrices is that we want to translate what we see geometrically into the language of algebra. Why do we need to translate into the algebra to the language of algebra? So that we can devise something which can be used like a black box. Eventually that is the goal. Right now what we are doing is we are building a black box. Of course, when you build it, the black box is not black. We know very well what is in there because we are putting everything inside the box. Once it is done, the idea is we can actually forget about everything and use it like a machine. But to go there, we have to digitize everything. We have to put numbers and expressions for everything. That is why we need matrices. And since we are going to use matrices to such a great extent, it is imperative that we know all about matrices. So, that is the purpose of today's class and the next class. The name is actually very accurate. Today we will only get to know our matrices. What they do is going to come later on. So, that is what we will do. We will just familiarize ourselves with some kinds of matrices which you perhaps know already, right. But even before that, do not forget we have some unfinished agenda from the previous class, right. And what is the unfinished agenda? We had just about started talking about similarity transformations and class. Okay. So, we might as well go ahead and finish that discussion. And whenever we finish a discussion, we like to bring in an example from chemistry. Let us see whether we can do that as well. So, that numbers just do not remain lifeless numbers, but take some tangible form, right. So, this is where we had stopped in the last class, right, with the correction. There was a typo in the last one, here there is none. So, similarity transformation is defined as B equal to x inverse A x, and the condition is that A, B, x, all of them have to be elements of the group. So, if A and B are related in that way, that when you take A and then multiply it on the left side as well as right side by x and x inverse, then you get B, then you say that A and B are similarity transforms of each other. And the other word that is often used is conjugates. A and B are conjugates of each other, and they are related to this thing called class, because a class is defined as a complete set of elements that are conjugate to each other, alright. So, this is something that we had presented even in the previous class, right. So, since we are talking about similarity transformations, conjugates, let us learn about a couple of properties of conjugates. So, the first theorem is every element is a conjugate to itself, that is A equal to x inverse A x. Now, the question is what is x? Can x be anything? Any element in the group, or is there some restriction on x? Let us see. So, whenever we have something like this, what we like to do is we like to left multiply, right multiply, simplify. So, let us start with the left hand side and let us left multiply it by A inverse. Why will we left multiply it by A inverse? Then it becomes E, right. It is always better to work with 1, life is much simpler. So, left multiply by A inverse, what do you get? A inverse A is equal to A inverse x inverse A x, right. Now what do? Now we need to work with the RHS, A inverse x inverse Ax, A is there, x is there, their inverses are there. So, is A inverse x inverse of Ax or not? Let us see. Will you agree with me when I say A inverse x inverse is the inverse of XA? Right? That is very simple, right? X inverse x is E, then EA is A inverse A is E. Very simple. So, it is not very difficult to see that A inverse x inverse is the inverse of XA. XA not AX, alright. So, let us take that and let us plug it in into the right hand side. You get XA inverse multiplied by AX, okay. I hope we have not forgotten what left hand side is. Left hand side is E. So, if left hand side is E, then right hand side also has to be E if this has to be correct, right. When is the right hand going to be E? When XA is the inverse of AX. When will XA be inverse of AX?
When AX equal to XA.
When A and X commute, right. Is it necessary that you will have an element in the group which will commute with A for any group for any A? Is it necessary that there will be one element in the group that will commute with A? Identity has to commute, right. So, if nothing else, X can be equal to E, right. And then if there is anything else, then the more the merrier, does not matter. But the point is that even if there is no other element, E serves the purpose. E inverse A E is equal to A. Is that correct? What is the inverse of E? E itself. So, EAE, what is that? That is still A, right. And as we have said that identity is an essential property, essential condition for formation of group. So, E has to be there, you cannot do without E, alright. So, every element is a conjugate to itself. Now that we have done the proof, it sounds kind of silly, trivial, right. But when we started stating it, perhaps it did not. Fine. Now, the next one is somewhat like the 0th law of thermodynamics. If A is conjugate with B and C, then B and C are conjugate with each other. If I just write down this line in a mathematical form, is going to be A equal to x inverse Bx and A equal to, let us say, y inverse Cy, where x and y may be same, may be different, I do not know yet, okay. Same is a special case of different. So, it is better to start with different, fine. So, now will you agree with me if I write B equal to x A x inverse? What have I done? I have left multiplied by x and right multiplied by x inverse, right. So, left multiplied by x, x inverse becomes E, right multiplied by x inverse, x inverse becomes E. So, I am left with B and here it becomes x inverse A x inverse, alright. Now, what will I do? I can plug in this value of A into this, right. A equal to y inverse Cy, right. What am I trying to do? I am trying to find the relationship between B and C. Okay, so, it makes sense to eliminate A from the expression of B and substitute it by C. So, I bring in that, what do I get? I get x B equal to x y inverse C y x inverse, alright. Now, will you agree with me if I say x y inverse is the inverse of y x inverse? Just multiply x y inverse y x inverse, y inverse y is E, so you do not have to write it, you are left with x inverse, that is also E. So, x y inverse is the inverse of y x inverse, alright. And just for the sake of simplicity, I will write z equal to y x inverse, alright. So, what do I have here? what does this become? B equal to Z inverse C Z. And therefore, what we had stated to start with, it is proved that if A is conjugate with B and C, then B and C are conjugate with each other, right? Simple. Good. Now, so now that we know a little bit about conjugates, let us talk about class. A class, as we said earlier, is a complete set of elements that are conjugate to each other, right? And this is best understood by taking an example. So let us refer to our old friend G6 number 2, and this is the multiplication table that we had shown in the previous class. In what context did we discuss G6 subgroups, right? So we said, what are the subgroups here? EA, EB, EC, and then EDF forms another subgroup. And what is this related to? What was the chemical example that we used? Yeah, but I did not talk about a G6, did I? Okay, fine, we will do it today, right. So now let us see, let us find the complete set of elements that are conjugate to each other. What will I do? The only thing I can do here is brute force. I will take every element, work it out, right. So since it is a lot of work, I will not do it, you will do it. I will only ask the questions, you are going to give me the answer. So here goes the first question. What is E inverse AE? Stupid question. We know already. What is the answer? A. Very good. Next one, A inverse AA, that also is easy, right? A inverse A is E, E into A. See, I said it is a lot of work, maybe it is not. A. But then it is not also as easy as it might have seemed so far. So, this is a very common strategy of marketing, right? Show the good points first and then attract people and then make them do things that they may not want to do. So, let us do this. B inverse AB, this you have to work out. What is B inverse? B inverse is B, B, B. Oh, then it is easy perhaps. And then what is AB or BA? AB will be what? A, B, that is F, and B inverse F is B, F, C. So now comes the first useful information, something that we did not know so far, right? That A and C are conjugates to each other. Okay, so A and C should belong to a class. Next, C inverse, yeah. They belong to a class. Let us just keep it there. Then we will see. Of course, since there are similarity transformations, some similarity has to be there, but we will see what that means. C inverse AC, what is the doubt? B, okay, good. Next is D inverse AD. You see what we are doing? We have taken A and then we are using all other elements, right, to similarity transform A and see what we get. D inverse AD, B. Rapid fire does not always work. Finally, F inverse AF, C. So, what does that mean? A, B, C form a class, will you agree with me? A, B, C are conjugates of each other and they form a class. Do you agree that A, B, C are all conjugates of each other? But here I have shown that A and C are conjugates and A or B are conjugates. How do you know that B and C are conjugates? Because we just proved it. Do not forget, column first, row second. In a product, column first, row second. You had that confusion? I have had that confusion for a long time. Even now I get confused from time to time. So, you are in good company. I think it is G6 2. We did not discuss G6 1. We did not work out G6. We have just taken it from Cotton's book. Alright. So, using the theorem that we know already, that if A and B are conjugates, A and C are conjugates, then B and C also have to be conjugates. We see that here A, B and C form a class of order 3. Alright. Now, what is left? D and F. Now, do not think that D and F must necessarily form a class. They might be classes of their own, you never know, alright. But let us see. E inverse E is D. A inverse DA, what is that? A inverse DA. F. So, D and F are conjugates to each other, and I think you can guess the remaining part of the answer. No matter what you do, if you start with D, you will get either D or F. B inverse DB is F. What is C inverse DC? What is D inverse DD? That is very simple. Yeah, it better be D. Okay. F inverse DF. F inverse DF. D, all right. G inverse DG. There is no G, right. So, there is no point in talking about G inverse GD. So, what does this mean? That means that D and F form a class of order 2, right. Question? Question? Yeah, ask. All right. E is a class of its own, because we can prove x inverse Ex, what will that be? Ex is x, and then you have x inverse X is E. So, no matter what you use, A, B, C, D, X, Y, Z, P, Q, R, S, E will always transform into E. So, E is a class of its own. Column first, row second, top first, side second in the product, right. And see, now look at the numbers. What is the order of the group? Order of the group 6. And what are the orders of the classes? 3 and 2, 3 into 2, 6. It is almost becoming numerology, right. Orders of classes are integral factors of the orders of the group, pretty much like the orders of the subgroup. You can prove it in the same way, right. But now the question is, what is this ABCD? Does this make any sense? Let us see if it makes any sense. Can you think of some point group which could be G6? G6 means how many symmetry operations? 6 including E. So, have we discussed any molecule, any point group that has 6 symmetry operations? C3V, right, and C3V happens to belong to G6. Okay. So, here you see what are the operations that belong to the class. Can you now substitute in this multiplication table and convince yourself that C3V multiplication table is indeed like G6 2. So, instead of ABC you can write sigma VA, sigma VB, sigma VC. Instead of D and F you can write C3 and C3 square. Of course, I am dictating this order because I know the answer. Okay. If you do that, let us at least check some elements. Okay. What did we say? We said that D is C3 and C is one of the planes. Okay, let us make it even simpler. D is C3 and F is C3 square, right. What is the product D and F? E. Let us see, D and F is E, F and D E. Okay. That is why I said that. Now, what about these three EAB? A, what is the inverse of A? A. What is the inverse of B? B. What is the inverse of C? C. Now, think of a reflection plane. What is the inverse of a reflection operation? Reflection in the opposite direction, basically same, right. So, that is why it falls in place. So, we have three reflection kind of operation here and two operations that are like rotation, C3 and C3 square. Okay. Work out the multiplication table of ammonia C3b, you will see you will get the exactly the same answer, alright. Now, see, now what are we saying? We are saying that ABC form a class of order 3. What is ABC? What did you say? The 3 planes, right. So, ABC, the 3 sigmas belong to a class and C3 and C3 square belong to a class. I think Prabha had mentioned class of symmetry operations in one of the previous classes. You are saying class too many times, one of the previous sessions, days, whatever. Huh? So, this is what is the meaning of class even of symmetry operations. So, what does this mean? It means that if you take the reflection operation of any plane and perform a similarity transformation, what should you get? Let us say what are the planes ABC, right. So, if you take A and perform a similarity transformation using the other planes or using C3 or C3 square operation or using identity, what should you get? Or you could get itself, no? Remember? So, see, when you use E to perform the similarity transformation, you get A. When you use A itself, then also you get A. Okay. When you use anything else, now do not forget A, B, C are the planes, right. D and F are rotation. Even when you use rotation, you get some plane, alright. Even when you use the rotation operations to perform the similarity transformation, you start with a plane, you get a plane, you get a different plane, yes, with rotation. And same is true for the rotations. Do not forget A, B, C are the planes. Even if you use the planes to perform the similarity transformation, you do get some rotation only, nothing else, alright. So, this then is the chemistry example, right. So, ABC, the 3 planes belong to one class, D and F belong to another class. Okay. So, earlier we had defined class in a little different manner. What did we say? What was the definition of class that we used earlier? Class of symmetry operations. When do symmetry operations belong to the same class? Yeah? That is now. What about earlier? Earlier also we said something, right? When we were talking only about symmetry, when we were innocent of the knowledge of all these numbers. How did we define symmetry operations in the same class or equivalent symmetry operations? Same character will come, but same character is something that we have demonstrated already, right? Same character, right? But even easier example, when you apply another symmetry operation, then this symmetry operation gets converted to another symmetry operation of the same class, right. So, what we said is when you apply C3, then A becomes B, B becomes C, C becomes A, where A, B, C are the 3 planes. Similarly, when you apply one of these planes, then C3 will become C3 square, right. So, this then are the three different ways in which you can think of a class of symmetry operations. First is, do they interchange upon some other symmetry operation, that is the simplest. Second is, when you look at the matrices and look at the character of the matrices, do they have the same character? That of course is something that we have proved only kind of we have demonstrated, we have not proved, right. We have only demonstrated using one example that the operations belonging to the same class have the same character. And now we learn the more formal, most formal group theoretical definition, that symmetry operations or anything belong to the same class when they are similarity transformations of each other. Of course, this definition is not restricted to symmetry operations alone, it is true for anything. If you have a set of numbers in which you can do symmetry similarity transformations like this, they belong to the same class, all right.